Good morning, one and all. Myself, Vaidigi, working as Assistant Professor in Sri Muthukumaran Institute of Technology in EC Department. Today we are going to see the topic from the subject DSP Architecture and Programming, and the subject code is CEC 337 for the 6th semester ECE students under the regulation 2021. The Unit 1 topics are from the Architectures for Programmable DSP Processors. Before going to the topic, let's see about the overview of the DSP architectures. Digital signal processors, commonly called DSPs, are specialized microprocessors designed for high-speed numerical computations. They are optimized to handle repetitive mathematical operations efficiently. DSPs are mainly used for real-time signal processing applications. Examples include audio processing, speech processing, image processing, radar, and communication systems. Unlike general purpose processors, DSPs are generally designed to process large volumes of data continuously. They support fast multiplication and accumulation operations. Real-time performance is a key requirement in DSP systems. DSPs must process input samples within the strict limit times. To achieve this, their architecture is highly optimized. They use parallelism and specialized hardware units. This slide introduces the basic concept and application of DSP architectures. Understanding this is essential before studying material of the DSP internal components. Next, see about the basic architectural features. A programmable DSP device provides instructions similar to a conventional microprocessor. However, it is also includes additional features optimized for signal processing. The instruction supports arithmetic operations such as addition, subtraction, and multiplication. Logical operations like AND, OR, NOT, and XOR are also included. One of the most important operations in DSP is multiply and accumulate, or simply we call it as MAC operation. Signal scaling operations are used to control data magnitude. DSPs include on-chip registers to store intermediate results. On-chip RAM is used to store signal samples. On-chip RAM is used to store filter coefficients and constants. These features reduce memory access time. Overall, the architecture is designed for speed and efficiency. These features distinguish DSPs from general purpose processors. In the next slide, we see about the DSP computational blocks. DSP architecture consists of several specialized computational blocks. The most important block is the multiplier accumulator unit. It performs multiplication and addition in a single instruction cycle. The arithmetic and logic unit, or ALU, performs arithmetic and logic operations. Shifters are used to scale numbers by shifting bits left or right. Registers are used to store temporary and intermediate data values. A program controller manages instruction execution and sequencing. These blocks operate in parallel to improve the performance. Parallel execution is a key feature of DSPs. Each block has a specific role in signal processing. Together, they enable fast computation. Efficient interaction between these improves throughput. This slide explains the internal architecture of the DSP processors. Next, we see about one of the computational block, that is multiplier. Multipliers play a crucial role in DSP systems. Early processors used shift and add multipliers, which were slow. Modern DSPs use single chip parallel multipliers. These multipliers can complete an operation in one processor cycle. Parallel multipliers are also known as array multipliers. They significantly improve processing speed. This allows DSPs to handle real-time applications effectively. While designing multipliers, accuracy is an important factor. Dynamic range determines the range of values that can be presented. Speed is critical to meet real-time constraints. These parameters influence DSP performance. Efficient multipliers are essential for filters and transforms. Hence, multipliers are a core component of DSP architecture. Next computational block is the shifters. Shifters are used to scale data values in DSP processes. They can shift bits to the left or right. Left shifting increases the magnitude of a number and the right shifting reduces the magnitude of the number. Shifters are used to prevent overflow during arithmetic operations. When adding n numbers, the result can exceed the accumulator size. Scaling is avoided to overflow errors. Similarly, multiplying two n-bit numbers can produce a 2n-bit result. Shifters help manage this increased word length. They are also used in normalization operations. Shifters improve numerical stability and the proper scaling ensures accurate DSP computations. Thus, shifters are essential for safe and reliable processing. Next slide is about the multiply and accumulate unit. Most DSP algorithms involve repeated multiplication and additional operations. Examples include FIR filters, IIR filters, and convolution. To efficiently perform these operations, DSP use a multiply and accumulate unit. Simply we call it as MAC unit. A MAC unit combines a multiplier and a accumulator. It computes the operation A is equal to A plus B cross C. This operation is completed in a single clock cycle. The accumulator stores intermediate sums. This greatly improves computational speed. MAC units reduce instruction count. They also reduce memory access overhead. This makes DSP processors highly efficient. MAC units are the heart of DSP architecture. Almost every DSP application relies on MAC operations. Next computational block is the arithmetic and logic unit. The arithmetic and logic unit or ALU is a fundamental component of DSP architecture. It performs arithmetic operations such as addition, subtraction, increment and decrement. It also performs logical operations like AND, OR, NOT and XOR. The ALU supports both signed and unsigned arithmetic numbers. These operations are essential for data manipulation. The ALU works closely with registers and memory. It processes operands provided by registers. The result is stored back in the registers or memory. The ALU operates at high speed. It operates single cycle execution for many instructions. Efficient ALU operation improves overall DSP performance. This unit complements the MAC unit in DSP systems. Next we see about the bus architecture and memory. In that we are going to see about the von Neumann architecture. In conventional microprocessors, von Neumann architecture is used. In this architecture, a single memory is used to store both program instructions and the data. A common bus is shared for instruction fetch and data access. This creates a bottleneck known as von Neumann bottleneck. Only one operation can occur at a time. Program bus fetches instructions from memory. Data bus transfers operands and results. Address bus identifies memory locations. Due to shared memory, speed is limited. This architecture is simple but inefficient for DSP applications. Real-time signal processing requires faster data access. Therefore, von Neumann architecture is not ideal for DSPs. This limitation led to the development of improved architecture. To overcome the limitations of von Neumann architecture, Harvard architecture is used in DSPs. In this architecture, separate memories are used for program and data. Separate buses are provided for program and data access. This allows simultaneous instruction fetch and data execution. As a result, processing speed is significantly improved. Harvard architecture supports parallelism. It reduces memory access delays. DSP processors often use modified Harvard architecture. This combines flexibility with high performance. Separate address buses further provide efficiency. Harvard architecture is well suited for real-time DSP applications. It is one of the key reasons for high DSP throughput. This architecture is widely used in modern DSPs. Next we see about the data addressing capabilities of DSP processor. DSP processors support advanced data addressing modes. Immediate addressing provides the operand with the instruction itself. The direct addressing specifies the memory address explicitly. Indirect addressing uses registers to store memory addresses. Circular addressing is used for continuous data buffers. It is especially useful in FIR and IIR filters. Bit reversing addressing is used in FFT algorithms. This helps in efficient data reordering. These addressing modes reduce software complexity. They also reduce instruction count. Efficient addressing improves processing speed. DSP addressing modes are optimized for signal processing algorithms. They provide flexibility and efficiency. This slide highlights the importance of advanced addressing techniques. Next we see some of the examples of DSP architecture. Several commercial DSP architectures are available today. Texas Instruments C6000 series uses VLIW architecture. It provides very high throughput through parallel execution. Analog devices, sharp processors support float point operations. They are used in high precision applications. Motorola DSP 56300 series is a fixed point DSP. It is suitable for cost-effective applications. Each DSP architecture is optimized for specific requirements. Choice of DSP depends on application. Its factors include precision, speed, and the power consumption. These examples show diversity in DSP designs. Understanding these architectures helps in system selection. They illustrate real-world DSP implementation. Finally, we see about the summary of the slides. DSPs are specialized processors optimized for signal processing. They are designed to handle real-time data efficiently. DSP architecture includes specialized units like MAC and ALU. Multiple buses enable faster data transfer. Parallelism is a key feature of DSPs. Advanced addressing modes simplify algorithm implementation. Harvard architecture improves performance significantly. Efficient multipliers and shifters enhance computation speed. DSPs are used in communication, audio, and image processing. Proper architecture selection is application dependent. Understanding DSP architecture is essential for programming DSPs. This unit provides the foundation for advanced DSP topics. Students, hope you all understand the content of my lecture. Next we see in the next video. Thank you.